Hello, everyone, and thank you for attending today's webinar, Why Design? I'm Billy Lute, Senior Editor of Solar Power World. Before we get started, let's go over some of the features of this platform that you can use throughout the presentation. You can submit, and you can still do this questions during the webcast. If we don't get to your question, our presenters may reach out to you after the broadcast. And lastly here, you can adjust the size of the slides on your screen using the icon on the top right corner of the slide widget. You can expand any of the on-screen boxes to fit your preference. If you encounter any technical issues with the presentation, try refreshing your browser. This tends to resolve most issues. If that doesn't work, try closing other applications and browser tabs running on your device. Additionally, you can click Help in the top menu for additional troubleshooting options. Or if all else fails, you can also ask us for help directly in the Ask Question widget. Thank you to PVFARM for sponsoring today's presentation. And now to introduce today's presenters. We are joined by Maxim Markovich, Head of Technology with PVFARM, and Jason Spokes, Senior Product Director of PlantPredict with Terabase Energy. And now I'll turn things over to Maxim.
Thank you, Billy. Appreciate, as always, pleasure to be here, guys. So let's start. So today we're going to be talking about why bankable energy should begin with a bankable design. We know that the industry works in a way that we are financing 25-year revenue streams based on energy assumptions made before even real layout exists. So let's start and see like what kind of market context do we have. So what we see in the news is that most of the solar projects, they're actually underperforming. At least this is what is being written about. If you guys have any ideas why we're not getting signals or why we're not getting articles about about solar projects that overperforming, please send those to us, to me and Jason, and we will basically choose the funniest and the smartest ones, and probably will send you some gifts. So the situation is that solar projects underperforming, and we will start basically with the question: what is bankable design? Because everybody knows what the bankable energy is, and Jason will explain it a bit later. But basically, let's talk about what bankable design is. So first of all, let's probably ask a question: why bankable design doesn't exist today? As you all know, the solar PV project development, it might take up to 2 years, and also detailed design and construction will probably take another 1 year, and then this project will be operating for 30 years or something. So there is a very narrow window during project development and where the decision about the financing being locked in. And this narrow window is typically very constrained in terms of time. So there are not much time, not much money to spend, not much expertise. Typically, expertise is about involving engineers of record, and other specialists as early as possible to start brainstorming solar PV solutions, and that's frankly speaking the time where this is not possible because it's the very beginning. So that's why it's actually, if you think about, would it be possible to come up with a very detailed design that early in the process? Probably not. But we will talk today about, first of all, what it is, bankable design. We'll try to come up with a good explanation about what it is, and then we will brainstorm about what can we do slightly better during this stage. So bankable design, we call a bankable design the design behind the energy model, which is basically site-specific, buildable, and economically grounded. And we'll go and talk a little bit about each one of those words. So site-specific. But design is a site-specific when it takes into account lots of context, right? In terms of context, it might be terrain, it might be some power lines, locations, highways, it's a soiling conditions, it's a flood depth areas, it's a velocity, scores, and many other things. That's, frankly speaking, the reason why construction projects, they are so complicated. because they've been placed within a specific site context. And you might actually, we hear quite often from engineers that working on the solar projects that they say, I never seen two the same projects. So, like you kind of think about, okay, what can be so different, because it's a solar PV layout, it's just the modules, panels, etc. But actually the site context is the main reason why it's hard to find two the same projects, because the site context basically defines how it's designed, what it looks like, and how much capacity it produces. So basically, site-specific design is a design that respects the context as much as possible. Obviously, it's not always possible to do it in the best way. It's not always possible. People not always have the data, like a very detailed terrain data. Sometimes hydrology wasn't, understood yet, or so geology doesn't exist at all. So that's why site-specific means that it takes into account the site's context as much as possible. So the second word in the bankable design definition is a buildable. So buildable design is also quite a, I would say, relative term. However, what it means is that it has those components that make this design look realistic, and that make this design what the most important, not actually not looking realistic or visually pleasant is not actually the most important part, right? So the most important part is that this design can be built in a real life, right? So you can buy equipment, you can use the grader machines, you can build this essentially. Typically, there are specific components that you can start noticing when you actually reviewing designs which actually say that this is a buildable. And in industry, I would say that people mostly define that this is buildable when they see meaningful roads, when they see entries, fence clusters, when they see specific buildable areas, wetlands, basins, laydown areas, when they also see a meaningful electrical groups like inverter blocks, transformer blocks, combiner groups, combiner circuits, load break disconnect circuits, proper racking, etc. So basically, buildable design is the design that are realistic to build, and it takes into account as many real components that you can buy, and also as many design solutions and requirements that you can actually fulfill and build on the construction site. So, and then the third word of and the third, I would say, criteria or dimension of the bankable design is that this design should be economically grounded. That means that you have a good understanding of how much would it cost in today's market, right? Not in terms of like benchmarks and comparing to the historical project, but in terms of those exact components we were talking during the buildable design definition, like roads, fences, low voltage cables, medium voltage cables, trenches, blocks, inverters, transformers, medium voltage circuits, sectionalizing cabinets. So all of those components, they have their own cost. And there are also many activities like around those, like installing equipment, installing cables, harnesses, whips, extenders, providing basically proper connections for all of those components. And when you start getting this insights and combine those into cost, that's the design that actually economically grounded. That means that it has components, and those components can be priced and put together and can give you a meaningful understanding of what would it cost. So let's just summarize one more time. So we call a bankable design a design that is basically site-specific, buildable, and economically grounded. And each one of those terms, it might be fulfilled in a different, to a certain level, right? Based on the data you have, based on the data available, you can actually, you can have a buildable, slightly less or more buildable, but basically those terms define the bankable design. And let's probably compare this to what we call simplified design, just a simple kind of table that shows that in simplified design, people typically don't consider structure like a specific, let's say, tracking manufacturers. They basically fill layout with strings. So tables orientation might be averaged. Well, for bankable design, it should be site-specific. Equipment should be placed on the terrain. terrain should be site specific, meaning that, having like I would say 10 meters resolution terrain is better than having no terrain, right? So civil constraints not modeled versus explicitly modeled, the same for electrical and energy modeling and shadowing. So that's the kind of the difference between what we see is simplified design and bankable design. So basically, one more time, bankable design is a design that based on a real context, real equipment, real cost distribution, and as close as possible to the reality performance model, right? And then the simplified design doesn't have those criteria. So with this being said, it basically we are not saying that simplified design is bad or and bankable is good. We are saying that basically that there is a difference between simplifications, and quite often we don't have a choice and we need to simplify things. We cannot design in a very detailed way, especially when there is no data to design around. But I think for the few further discussion about this topic, it was important to set those definitions. And with this being said, I will hand it over to Jason, and Jason will start talking about industry challenges.
Yeah, hi everyone, and thanks, Maxime. And yeah, so Maxime just made a case for why bankable design, which is site-specific, buildable, economically grounded, should inform a bankable energy model. But let's talk about a few of the challenges that we may face along the way, starting with a lack of context. And so what do we mean by context? So I'm going to define this as the business objectives, the assumptions, the constraints that define why a modeling or design task is being performed and how its results are going to be used. And the pitfall we sometimes fall into, and I'm certainly have been guilty of this myself, is really focusing on preparing the deliverable without fully understanding the business context that's driving the need for that deliverable. And just as a illustration, I'm showing kind of two designs of the same cathedral. So there's a simplified version on the left and a photorealistic version on the right. And let's just say that my deliverable is to estimate the dimensions of this cathedral. Well, the simplified design might be more than sufficient. On the other hand, if I need to estimate the labor hours associated with building this cathedral, I'll probably want something closer to the realistic design. And the point here, as I think Maxime said, is that when we want to translate or we want to bring information from the solar design into the energy model, the business context that's driving the need for that energy model is critical because it helps us focus on the design details that matter for that particular business context. And so let's take a look at a real example, in this case, inverter load ratio. So the plot on the left shows a distribution of inverter load ratios for a single project, ranging from 1.0 to 1.4, with a weighted average of exactly 1.2. And coming up with this distribution can be time consuming, although software like PVFARM can greatly reduce that effort. But it's important to recognize that the energy model, which assumes all inverters have the same average 1.2 inverter load ratio, is not the same as modeling the realistic distributions of load ratios within the performance model. And in this case, we can see that the simplified model overestimates annual energy by 1.5%, equating to an approximate $2 million in revenue shortfall on an NPV basis if this project were to be built under the assumption of the simplified ILR. And that's not to say that modeling an average ILR is always wrong. It really depends, again, on the business context for that energy model. For example, if we're trying to compare yields from two different modules on the same project and kind of deciding between two different modules, simplifying both models to use an average ILR might be perfectly acceptable. And really, just to sort of hammer it home, the goal is really to ensure that the design accuracy and detail are sufficient to meet the energy model business context. All right, let's talk about a second industry challenge, and this is related, and it's loss of data across transitions. So what do we mean by transition? So a transition could be a handoff between two different parties. So it could be internal or external stakeholders. It could also mean a migration or a translation between two different software applications. And today we're really focusing on the latter, which is the transition between the design and energy modeling softwares and how to maintain the business context that we spoke about earlier. And to kind of illustrate this, so, there are times where we have a very realistic, very detailed design, and we need to translate that into an energy model. And, oftentimes some level of simplification takes place. As design and engineering often take place in different software applications than the performance modeling. And so some type of translation needs to take place. And as a result, we may lose detail. So why do we lose detail? Why do we simplify? Well, sometimes, the energy model itself cannot accept a realistic design detail. Sometimes we lack the time and resources to recreate a high fidelity design in our energy model. And sometimes we may not fully be aware of the kind of accuracy benefits that bringing that high level of detail allows us to do. So moving on to a second example, let's take a look at, in this case, 3D racking slopes and orientations. So the plot in the upper right shows a distribution of racking slopes that was taken from PVFARM, ranging from 6% north facing to 6% south facing. And then you can see the sort of the locations of those different sloped racks based on the colors on the layout on the left. And as many folks on the call probably know, it can be really difficult and time consuming to reproduce that 3D design geometry in our performance model. And we're going to be talking about this specifically in the demo portion, software demo portion of today's webinar. But it's important to note that this can be one of the more consequential design elements due to some compounding kind of nonlinear factors that are associated with shading and different plane of array radiances for all of the different tilt orientations. From the table, we can see a 4% reduction in annual energy when we bring in this 3D design detail relative to the 2D simplified model. And that is really significant. And we can also see, one approach that people have done to try to bring some realism into the energy model is to simplify into prevailing slopes. And we can see that kind of moves us in the right direction, but is nowhere close to the full 3D sort of implementation. And with that, I'm going to hand it back over to Maxime to talk more about kind of how we see the solution and starting to get into the software demos. So.
Thank you, Jason. Appreciate. So Jason highlighted basically two cases, I would say, two challenges, right? There are many more. We just chosen those ones that are the most, bright in a way. But essentially, we were brainstorming together, like what kind of solution we can bring to the table and what kind of solution it might be to address those challenges. And to address the actual challenge which we highlighted at the very beginning, that we financing the projects based on assumptions when we don't have a detailed design, right? So the obvious solution would be, it's actually so obvious that it's even ridiculous in a way, right? Bring more design reality sooner. And it's a simple, but also it's beautiful in a way. And by saying that, we don't mean do more work or start spending money before you committed that you can buy that parcel for solar PV project or whatever else, which is basically saying that the market is evolving. There are new tools. There are much more automation that we had 5-10 years ago, right? There are more options to run a very sophisticated trade-offs, analysis, optimizations, etc. So basically, with having those tools, you can actually run a bit more, right? Even if you run a bit more, that means your design is more bankable. If you never did blocking at the early stage and then you started doing blocking, then it might be not a big of a difference in terms of time spent. It might be some education difference, but it just will add a little bit more bankability and reality to the design. So essentially, the solution we want to present today is bring more design reality sooner. And as Jason said, we're gonna do like a product demos right now, just a little bit. And what we're saying is that we cannot change the window, right? We cannot change that window, which we discussed in the beginning of this webinar during the project development. It's a tough, right? There is no money, no time. You don't have 50 people working on this project yet, right? So what can you do when you have those limitations? And as I said before, you can actually start exploring slightly more and adding a slightly details to the project. So let's basically go, and I'm gonna share my screen, and we'll talk about the bankable design and what it means. I hope you guys can see my screen, and I will start talking about PVFARM a little bit and about the definition of the bankable design, and what we've discussed is the design that is site specific, right? And when you say site specific, what it means is that basically essentially means that, let's say you took into account some the highest gradient areas, like you can see here highlighted on the block 9, block 4. It also means that you have a meaningful access to the parcels. So if I have my parcel on the right and I can see the road going from the substation, I might not have like all necessary details, but I can see that these roads come in this parcel and there is another road, which is, again, it might not be looking detailed at this stage, but but it depends what kind of data we have. And so we have this road, we know that there is a place for the truck to turn around and to come back. So it might be not as like real as in a kind of final design, IFC design, but then you can see access is provided. I can access those inverters, that inverter, and I can work with this. Same in here. You can see I have every single inverter, like this one central inverter, it basically knows what kind of tracker is connected to it, right? Every single tracker knows what kind of combiner box is connected to. And then we have a lot of cables in there. And then every single cable run from a combiner box to inverter, from a string to combiner box, and you have those meaningful kind of relationships. So you can actually, okay, so can you highlight the combiner groups for me? Can you highlight the inverter groups for me, right? So all of those objects are connected in a meaningful way, which basically means that it's kind of more buildable, access provided, and then lots of information about DC. We also immediately kind of getting more details in terms of like what's our low voltage losses, what's our medium voltage losses. So which again, that's the numbers. If speaking about medium voltage, like the way people do today is quite often is that basically there is a certain assumptions about losses. However, when we're talking about design which is slightly more bankable, like this design would have some idea. Would you say this is a kind of correct circuit? Probably not. There are a bunch of quite ugly trenches, being honest. But it definitely has more information than if it wouldn't have this information, right? So you can at least estimate approximately or conceptually that there is a trench. It's running all this way along this road. And so like what we're gonna do with this. So basically those considerations, they matter even if they are not perfect. And because like this is just gives you a little bit more confidence and a little bit more foundation for actually providing a meaningful cost estimation, right? So essentially site specific takes into account, lots of constraints of the site. You might even have a specific place, like if I get a real closer and if I get in a 3D dimension, you might, again, you have like trenches, cables, trackers, you can see where you have fill, you can see where you have cut, you can jump into kind of validation mode, you can check what's going on, you can see how much we've cut there, you can see some funny areas where the hills were untouched because of the grading. This actually makes it slightly more considerable. And then after that, everything goes into the cost model without you even thinking about this. Cables, trenches, low voltage, medium voltage, like earthwork, piles, racking systems, pile material, steel tonnage, etc. Right? So it's kind of like a holistic system where everything connected and design is site specific, more or less buildable as data allows, right? Or as the project stage allows, and then economically grounded. And usually when we say economically grounded, what we actually mean is that, this layout, the layout of solar PV design, where every single component, if I select any specific tracker, it has a lot of information, not only about, like the geometry, but also like a cost information, electrical cost information, module information. So this data is being accumulated in a bigger chunks on the blocks level. And what it means is that you can start seeing like the cost of the blocks. So basically, I can start seeing like what are the most expensive blocks. And also, like if you think about medium voltage or essentially like circuits, like medium voltage circuits, again, another example, part of the circuit in here is basically like, like when we try to distribute back the cost of the medium voltage circuit. So if you think about this, it's a cable plus trenches plus connectors plus everything like needed to make this possible, right? So we essentially we start thinking about, okay, what kind of block would be more expensive from a medium voltage standpoint? Is it 27 and 28? And then usually you kind of think about the block that further from the substation would be more expensive. But then when you actually start calculating cables, you can start see like what's the ratio between medium voltage cost and low voltage cost. And you can start having like a very surprising insights about what's driving the cost on your particular project. For this particular layout, we run like lots of different simulations, and I wanted to ask, like, this is a same project, two different layouts, and we can argue which one is more bankable, more buildable, which one is like more realistic, which one would be preferable. But essentially, what's important is that is the immediate like a cost feedback, right? So when we talked about bankable design, the third dimension defining bankable design was economically grounded. And essentially, in terms of cost, I want to highlight that there are, if you talk to someone like civil engineer and you ask, what am I the most expensive civil from a civil standpoint blocks, we would say, okay, this block number 5, block number 17 and 18, these are the most expensive from a civil standpoint. Then if we will start talking about structural, we will see the ugly block number 4, and then we'll see block number 3. You can see like lots of trackers exposed from a wind load standpoint. And again, how do you know that? Data, right? So again, if we go simply in our analysis and just basically choose our trackers and colorize those from a wind load standpoint, we will see that here we have a hugely exposed trackers. And what it means is that for each of those trackers, we actually start having much heavier piles, which is defined in the asset itself. And because the way this asset is designed, you can actually afford defining multiple configurations, right? And so because of that information, the costs show you the actual accumulation of the structural cost in here. The same would happen if you would have a flood depth somewhere and would need like a longer piles or like weaker soils, etc. And then from electrical standpoint, again, we check in the most expensive blocks and we see other blocks, right? So then the question is, in a solar projects, the people that are responsible for those disciplines are different people. And And it's really hard to combine all of this data together, and that's why we actually try to, to combine this. And for example, here we can see what are actually the most expensive blocks from pretty much global standpoint, right? And quite often those might not be highlighted by any team, but also quite often they basically match. And all of that, speaking back about design being realistical, meaning, and here I just want to highlight a couple of things that Jason mentioned. The trackers and pretty much every single object is actually located the way it is. So if it's placed on the terrain, I can simply start checking, okay, how many north facing, how many south facing I have, right? So then maybe I wanna start checking my slopes, right? And I can see, okay, this is my slopes, and I can see that a specific slope for every single tracker, which is not averaged, quite detailed. So this basically layout, it might be not ideal, right? But let's say when you had just a couple of hours and you produce layout that have those many components in it, right? It's important to calculate the energy, taking this into account, right? Taking the exact blocks we had with exact inverter load ratio, taking into account the trackers basically installed on the terrain in a specific way with a specific slope. And here where we actually build into basically PlantPredict, and where we send the kind of the model, the very complicated model with lots of details to the PlantPredict, which we're going to do right now virtually. And Jason will present in a second what we can do with this further. So basically I'm selecting it here, export it, save this to my computer, and send it to Jason, so we can start talking further about all of that. So I'm going to stop sharing. Jason, it's up to you.
Yeah, thank you, Maxime, for that. And let me share my screen because I'm going to take us into PlantPredict. And okay, so everybody should be able to see my screen at this point. I'm sharing PlantPredict. So for those of you who are not familiar with PlantPredict, this is a performance modeling software, so we are able to define projects. We also have weather, inverter, and module libraries. Right now, I'm in a project called Joint Webinar 8460, and I've created 2 predictions already. Think of a prediction as basically a simulation. And in this case, I've got a 2D average inverter load ratio prediction. This is kind of a simplified baseline version. And I've got a complex 3D inverter load ratio distribution with a full, every inverter has its sort of realistic inverter load ratio associated with it. Whereas in the 2D version, we've got sort of 1.212 inverter load ratio for each inverter, for all of the inverters. Now, I've kind of already done some pre-work here because I've got limited time, only about 10 minutes to give a demo. So I admit that I've sort of pre-entered some of the data. Let's step into this complex 3D inverter load ratio prediction. And again, for those of you who are not familiar with PlantPredict, within the prediction, this is where we can define weather data. We can bring in time series data. So think of time series data as being measured data. So for example, if I'm taking surface temperature, module surface temperature measurements, or tracker angle measurements on site, I can bring that data into the prediction. I can also define the PV blocks and arrays. This is probably the most complex portion of PlantPredict, where we're really defining the plant. We can define the plant on a map, or we can define the plant sort of as a block builder approach. We're doing the block builder approach today. This is kind of akin to a PVSys workflow. We're treating PVFARM as really the design and engineering space, and we're bringing that into PlantPredict. The 3D scene is where we'll spend some time today. Energy storage system, I'm leaving off for today. System details, this includes, interconnection, substation transmission details, and model choices where we can select different submodels for the energy simulation itself. So one of the things I want to start with is within the PV blocks and arrays, I could go into this, and it's quite complex, and there's a lot of information to enter. I'm going to really start with what's called the Quick Edit tab. And this gives me a tabular view of all of my you can think of them as the inverter blocks. So within PlantPredict, we call them arrays, but these are basically the PCS blocks. So it includes all of the DC, the inverter, and the medium voltage step-up transformer associated with that block. And we can see that we've got 17 unique arrays or PCS blocks. And this is the quantity of each of those. So we can think of these as a unique inverter load ratio. And what I've done is I've taken the information from PVFARM and I've manually entered it on this screen ahead of time. So you didn't have to wait the minute or two it took me to enter this data. So just to elaborate a little bit more, so in this case, we've got, two PCS blocks, each with one inverter. The inverter is a 3.6 megawatt inverter. And sorry if the font is a little bit small here. And we can see the DC capacity associated with that inverter. And from that, we can get to the inverter load ratio. And you can see that the DC capacity is the variable that kind of ranges. So this is really just meant to sort of show where the sort of complexity of the inverter load ratio data that we took from PVFARM is coming into play. Now, I did enter all of this manually, and PlantPredict and PVFARM are working together to further integrations where we can bring this data in automatically. But for now, it's a manual process. And now let's move into the 3D scene, because that's where up to now we've really been working closely with the PVFARM team to make sure that we can import 3D data with the right sort of context. So when we come into the 3D scene, we can either upload a PVC file or we can upload an SHD file. It's recommended to go PVC file. One of the things that we've been working on recently, even as of this week, was geolocating that PVC file. And so I'll show you kind of what that brings to the table. Now, when we first upload our 3D scene, we're given a 3D scene overview page where we can configure certain 3D settings. Let's go straight into the scene itself. And it looks okay. And so now one of the things that you can see is that we've brought in, because this is a geolocated scene, we've brought in the underlying imagery to be able to visualize this scene in 3D. And we can see that it's definitely got undulation within it. And this is really the same geometry that was designed in the PVFARM space that has been brought in into the performance model. Now, we can inspect this by looking at different times of the day and looking at what the shade looks like on the racks at different times of the day. So at 8 a.m., 9 a.m., we still have a little bit of shading we can see here. Now, this is a standard backtracking algorithm. There are a lot of different tracking algorithms that we can bring into this model, including our own custom, if you want to specify tracking rotation angles for every time step, for every rack, it is possible to bring that in. And I'll show what that looks like in a minute. But let's zoom out for a second. And, one of the things I could have done in PVFARM is define shading objects like tree lines. We didn't do that in PVFARM. Let's do that now. So I'm going to define a couple of tree lines, and I will just sketch these out real quick, and hopefully you can kind of see me do that. And so we've put a tree line over there, and let's put another tree line over here. Okay, so you can see that we've sort of defined some tree lines, and it's possible to define different types of objects within the scene. and we can inspect and see the sort of shadows cast at any point in the day. And by the way, the time steps that we have in the shading simulator are really based on the weather file that's been uploaded. So if you're uploading a sub-hourly weather file, it is possible to inspect this at a sub-hourly interval, right? Okay, so we've sort of loaded our 3D scene. Let's save the changes and step into that. And let's run the calculations. Now, while the calculations are running, let me explain a few things. This is where we can define different tracking rotation angles. So we have some 3D options. We can define, like I said, a time series schedule where we're supplying all the track angles for every single rack. We also have a PlantPredict terrain-aware backtracking model. So we can think of these as kind of 3D models, if you will. Right now, it's pointing towards a target DC field. And in that target DC field, we have defined the tracking algorithm as a standard backtracking, which is indicated here. We also have the true tracking, we have irradiance optimization, and we do have Linstow models, which can be tacked on top of just sort of a standard backtracking model. But to keep it sort of apples to apples with the 2D version of the model that we had, that I had previously created, I'll leave it as a standard backtrack. Now, when we queued up the calculations, what happened was we first calculate the orientations. In this case, the orientations have already been preloaded because this is a standard backtracking model. If we had chosen a terrain-aware backtracking model, it would try to avoid shade in 3 dimensions, and those orientations would have to be calculated first. Next, it calculates the transposition, which is basically the plane of array irradiance at every tilted orientation in that scene. Then we do the shading calculations, which calculates the shade object shape on every shade, on every, let's say, tracker, as well as the nonlinear shade electrical effects. And you can see that for full precision, this was an 8760 time step simulation for a 120 megawatt project. Those calculations finished in under a minute. And let's go in and we can inspect the results. We'll look at this on a heat map basis, and I'll put it on a relative heat map scale. And we can definitely see some impact relative to the shade objects. Right now, I'm looking at the beam irradiance shade loss, but I can also look at the shade electrical effect loss, which is more distributed, the plane of array, the transposition loss or gain. Now, what's interesting about the plane of array is we can actually have gains where the south-facing sloped racks actually outperform sort of a 2D, think of a sort of theoretical 2D world. And then we have some, the orange racks would be sort of north facing. Okay, so I'm going super fast, I understand. I'm gonna step out of this, I'm gonna go ahead and run the prediction. Now, when I run the prediction, all of the results, all of the 3D results are brought automatically into the prediction itself. And these are included in the overall sort of energy calculations for every time step for every rack. And we've got, I think, 17 unique inverter load ratios. So usually a prediction takes, a second or two to run. This is going to take a couple of seconds more. So we'll wait for this to finish, and then we'll compare the sort of simplified 2D and the 3D. So I could go straight into the results here, but let me step out and I will directly compare multiple results. So I'll compare the 2D versus the 3D. And so on the left-hand column, I've got the 2D version. On the right-hand column, I've got the 3D version. Let's scroll down to where it gets interesting, which is plant net energy. So on the simplified 2D, I'm at 243.3, and on the complex 3D, I'm exactly 230.0. And I think if we did the math, that's probably around 5 or 6% delta between those two different cases. All right, again, I know I went super fast through that, but hopefully that illustrates how pretty straightforward it is to bring that sort of 3D complex reality and bring information around the inverter load ratio into PlantPredict and model that pretty quickly. All right, so I'm going to stop sharing and go back to the slide deck. And I wanted to wrap up with this particular slide. And so this is the last slide of the planned content, and really just wanted to say, we've sort of taken the time to kind of, Maxime's walked us through what a bankable design is, but we haven't really defined a bankable energy model. And this term gets thrown around quite a lot in our industry. I'm going to try to provide my sort of insight into what really constitutes a bankable energy model. First and foremost, the energy model needs to be informed by a bankable design, and that's really the focus of today's webinar. This energy model is typically built in a trusted, validated, reputable software application, of which there are several in the industry, including PlantPredict, that models the physics from the sun to the grid and uses typical meteorological data, also from a trusted, validated, reputable source. This physics-based modeling is really the primary driver of what's called the P50. P50 is sort of another way of saying the expected median production, or the 50% probability of exceedance production. It's maybe a little bit more complicated than that, but I think for today's discussion, it's very reasonable to think about the P50 as being really the physics-based yield estimate. But the P50 is only part of what lenders need to evaluate the project's cash flow and set credit terms. Really the P90, the P95, the P99, depending on the particular financial institution, establishes downside risk because it factors in things like weather variability, various model input uncertainties. These could be these could be internal uncertainties, these could be external uncertainties such as grid availability, as well as the underlying uncertainty of the software model itself. And just to sort of frame this, so PlantPredict and PVSys both have kind of simplistic PXX, P90, P95 calculators. Both of those software packages really focus on kind of getting the P50 right, getting the performance, the physics-based performance model right. They both have kind of simplistic, P90, P99 calculators, which are good for serving as indicative estimates, but are generally not sophisticated enough for being accepted by lenders. On that specific point, I do want to make a brief call out to the fact that PlantPredict is launching an integration in just a few weeks with an application called PowerUQ, which provides a Monte Carlo-based uncertainty quantification, which is in line with lender expectations. Look for a webinar on that integration for months in April. And really lastly, in the US at least, and I know things are a little bit different outside of the US, but in the US, lenders require these production estimates to be prepared by an independent engineer, i.e. With a trusted track record and one that has been pre-qualified by that lender. Notice I did not put a fourth requirement that a specific software must be used. In my experience, it is really the decision of the IE to select the software application that they believe is most appropriate based on their expertise. And with that, I think that wraps up our planned content, and I think we can move to the Q&A.
All right, yeah, we're going to open up the floor for some questions. We'll leave this slide up for y'all in case you want to scan and check out either PVFARM or Terabase. All right, so first question we have on deck, why do you think PVFARM can produce more bankable designs compared to other market solutions such as PVCase?
Okay, I think I will take this one. PVCase is a great tool. It's a native CAD plugin basically, and obviously you can go in a very detailed design, and you can build pretty much very detailed drawings and issued for constructions, etc. Right? So the difference, I would say, between PVFARM and PVCase is that PVFARM is a really BIM software built specifically for solar PV. And what it means in practice is that it combines really multiple areas of expertise together. So when you make layout, you get quantities, not only of equipment, but quantities and bill of materials for low voltage, medium voltage trenches. You get losses automatically calculated. You move the cable, the specs are being updated. You change something, basically the project metrics being updated, energy recalculated, shading recalculated. It's just basically a tool which is basically holistic building information modeling software built specifically for solar PV. So in that sense, it's just faster to get to quantities and bill of materials, and basically that's why you have a quicker feedback loop in terms of like, what among my blocks are the most expensive? Which combiner box circuit has the worst voltage drop? Where do I have the cables that I should not have? Like, you basically get a faster feedback loop because of this rich information data environment. But other than that, and I think when at the beginning stage, when decisions, like making those decisions based on real trade-offs is very important, that's where the PVFARM is quite advantageous. But that's been said, respect to PVCase, great tool.
All right. Next question. One of the challenges we're seeing is designing and modeling plants to comply with recent IRS 48E requirements for domestic content, where different module types may need to be installed on the same inverter MPPT. Can this be designed in PVFARM and modeled in PlantPredict?
I can take the PlantPredict part of that. Do you want to take the PVFARM, Maxim?
I'll join.
So I can say on the PlantPredict side, it is absolutely possible to model two different, let's say, module types on the same MPPT. So the inverter will try to find the common operating point between those two different voltage, IV curve profiles associated with those two different modules. Yeah, so that's more than possible to do on the PlantPredict modeling side. Maxim?
Yeah, sure. Basically, same story in terms of PVFARM. Again, we were building this engine for like many years, and the whole point was to build a software where you can easily swap modules, inverters, trackers. You can use simultaneously, single axis trackers, fixed tilt systems. You can start changing modules on those trackers, and you can start using multiple different modules under the same inverter. So no problems with that. Was built by design like that. Really great question.
All right, we had a couple questions regarding this. What types of further integrations are you planning between PlantPredict and PVFARM?
Jason, you take this one.
Yeah. So first of all, I think we see a lot of opportunity. We know that the industry is seeing a lot of value in terms of designing their plants in PVFARM. PlantPredict is natively able to, because it's API accessible, natively able to talk to other software applications. We see a lot of our customers pushing us in the direction of creating integrations with PVFARM. I think the vision is to move towards a more tighter integrations where you can push design information directly to PlantPredict and then receive energy data back into PVFARM. We really started with the kind of PVC compatibility as we move towards a PVC 2.0 sort of goal. But that's kind of really just a first step of our teams working together. we do see actual software talking to each other in the future.
All right. Would you agree that the market cares more about energy model risk mitigation than accuracy? And how do we change this?
Yeah, that's a great question. So I think from a project financing perspective, making sure that by mitigating risk, you help to sort of reduce the sort of energy delta between your P50 and, let's say, your P90. So that ratio of P50 to P90 starts to get kind of closer to 1. And that's really advantageous. I would say that what's really critical, though, is that P50 sort of defines that sort of central stake, if you will, where the P90 sort of expands to the left and to the right of that. And so making sure that you're starting with the right P50 is almost equally as important as really mitigating risk, because even if you can really reduce the sort of uncertainty of a lot of the input variables, if you get your P50 wrong, it kind of makes that distribution around that P50 less accurate as well. So hopefully that answered the question. It's a good question.
All right, next up. On PlantPredict's 3D scene, are there mounds that were not graded on PVFARM brought over to the 3D scene? If not, how could I bring those 3D features to PlantPredict?
So I think the rack profile. So within PVFARM, you can do grading of the surfaces. Basically the surface. And so the rack profiles on that graded surface are brought into PlantPredict. Now, the terrain itself from PVFARM is not currently brought into PlantPredict. So if you're talking about a mound that is not where a rack is placed over it, that sort of mound would not be, that would be part of a terrain that's outside of the sort of envelope of the racking system, would not be something that's imported in the PVC import. Now, as we go towards a PVC 2.0 sort of world, and if you're not familiar, there's a working group working on improving that kind of exchange format. I do believe that the terrain itself is possible to be defined in that file. And I would also say that in terms of far away kind of horizon profiles, that's defined separately in PlantPredict and from the PVC scene. Now, if you wanted to artificially sort of bring that sort of mound into the scene, you can do that. I demonstrated the ability to sort of define a wall, but you can also define cylinders and polygons, which have heights. It may not be perfect representation, but it is possible to bring some aspect of that into the scene.
Yeah, I would add here that basically that if you guys want to make this slightly probably more accurate, you can also double check. We have a conceptual. We are not obviously as focused on shading as Jason and PlantPredict, but we do estimate as well for shading, so we can have a look in both sources and compare and use it in a way so it's complement each other as well.
All right, I know we got a lot of great questions filing in there in the last minute, but that is all the time we have for today. If we didn't get to your question, our presenters may reach out to you directly following this broadcast. If you don't mind, please take a moment to fill out the survey that appears when this webinar concludes. We use your feedback to improve our future webinars, and this webinar will be shared with all registrants so you can view it again at your convenience. I'd like to thank our speakers for being here, and of course PVFARM for sponsoring today's webinar. And thank you to everyone in our audience for participating. We hope you enjoyed our presentation, and we invite you to join us for more Solar Power World webinars in the future. Thanks.